Can fire really burn water? Most people would laugh at that question. Fire burns, water puts it out. Simple. Well, what if I told you there's more to it than meets the eye? That question, strange as it sounds, is exactly the kind of puzzle I live for. Today, I'm going to take you on a journey where we explore this mind-bending idea and uncover the physics hiding in plain sight. You'll see how fire, water, and the invisible laws of nature can dance in ways you never imagined. Stick with me, because by the end of this video, your understanding of everyday things and the universe itself will be a little more explosive. Now, I know what you're thinking. Feynman, fire burning water? That's nonsense. And that's precisely why it's fun. Science is about asking the questions no one else dares to ask. I spent my life poking at nature, trying to pry out its secrets, whether it was in the quiet corners of a lab, the chaotic halls of Los Alamos, or even in the playful tinkering at home. Yes, it's a method to it, but it begins with curiosity, real curiosity, the kind that keeps you awake at night thinking, I wonder what would happen if... I want you to understand what we're really doing here. By the time you finish watching, you won't just know whether fire can burn water, you'll see the strange underlying physics that makes such a question not only possible, but illuminating. You'll understand why physics isn't just a collection of formulas. It's a lens for exploring the universe, a tool for solving puzzles that seem impossible, and a way to turn everyday phenomena into mysteries waiting to be solved. And if you pay attention, you'll pick up some of the ways I approach physics myself, as a detective, a magician, and a curious child rolled into one.
Let me tell you a little secret about myself that most people don't know. When I worked on the Manhattan Project at Los Alamos, I wasn't just calculating nuclear reactions, I was also figuring out how to crack safes.
That's right. In the midst of the gravest scientific project of the 20th century, I spent my spare time unlocking file cabinets, not to steal anything, but to understand the systems, to observe patterns, to learn how things really work. That's the essence of my approach: observation, experiment, and relentless curiosity. It's what led me to the discoveries in quantum electrodynamics that eventually earned me the Nobel Prize. And it's the same approach we'll use today to explore the impossible-sounding question of fire and water. So how does fire interact with water? You've always been told water puts fire out. But let's imagine a different scenario. Imagine water trapped in a sealed container, exposed to extreme heat. What happens then? You might expect chaos. You might imagine steam, explosions, or other dramatic effects. And you'd be right. But the story is richer than just a bang. At the heart of this lies energy, chemical reactions, and even the bizarre rules of quantum mechanics. Fire, under the right conditions, can do things to water that seem impossible. But that's exactly where physics becomes thrilling. And it's here, in the interplay between expectation and reality, that we see the power of a curious mind. Now, I could show you complicated equations or Feynman diagrams, but that's not necessary for this video. What matters is understanding the principles. Fire represents energy. Water represents a medium that usually absorbs that energy, and the interaction depends on conditions we rarely encounter in daily life. But by thinking carefully, imagining scenarios, and asking what if, we can see phenomena that challenge our intuition. That's what I loved about physics. It's a game of imagination grounded in reality. And in this video, we're going to play that game together. Let me take you further. I once explained to a group of students that if you heat water in a confined space, you're not just turning it into steam. You're creating a state of matter that behaves differently. Under certain conditions, atoms and molecules align in unexpected ways, and energy manifests in forms that can almost seem magical. It's a glimpse of the universe's hidden rules, a peek behind the curtain that most people never see. And the lesson here isn't just about physics, it's about thinking differently, asking bold questions and challenging assumptions. It's about curiosity. You'll still also learn how I approach these kinds of questions in my own life. I didn't just study the obvious problems. I asked, what do we not understand? What seems impossible? That mindset led me to discover new phenomena, develop novel experiments, and even enjoy physics in ways that most people think are only for geniuses. But here's the truth. You don't need to be a Nobel Prize-winning physicist to explore curiosity-driven science. You just need to watch closely, think creatively, and dare to question what everyone else accepts. And speaking of daring to question, there's a lesson in every experiment, even a thought experiment. When I asked, can fire burn water? I wasn't seeking fame or recognition. I was exploring the unexpected. And in that exploration, We encounter principles of thermodynamics, chemical reactions, and even the edge of plasma physics. You might be surprised at what you learn, and you might find yourself asking questions you never considered before. That's the thrill of science, the unexpected, the counterintuitive, the profoundly beautiful. So if you're ready to challenge what you thought you knew, to see fire and water in a completely new light, and to explore physics through the eyes of a true curiosity-driven mind, you're in the right place. Today on this channel, Feynman Flux, we're going to break down the impossible, play with ideas that seem absurd, and reveal the elegance of nature's hidden rules. And I promise, by the end of this video, you won't just understand the phenomenon, you'll see why thinking like a physicist is one of the most exhilarating ways to understand the world. Before we dive into the experiments, the thought experiments, and the surprising physics behind fire and water, make sure you subscribe to Feynman Flux. We explore science with the same curiosity and excitement I had throughout my life, and you won't want to miss a single mind-bending episode. Turn on notifications, grab a notebook, and get ready to think, imagine, and explore. So buckle up. Prepare to be surprised. Prepare to laugh, wonder, and maybe even gasp at the strange beauty of the universe. Because fire can burn water, not in the way you think, but in a way that reveals the astonishing truths of physics. Stick with me, and I'll show you how curiosity, imagination, and a willingness to question everything can turn a simple question into a thrilling adventure in understanding. Welcome to Feynman Flux. Let's get curious. Fire burning water, it sounds absurd, doesn't it? You've been taught since childhood that water puts fire out. That's just how the world works, or so we think. But in the universe of physics, especially the physics I love, the obvious answer is rarely the whole story. My name is Richard Feynman, and I spent my life chasing questions that seemed impossible, ridiculous, or even childish, because those questions often led to the deepest understanding. Today, we're going to explore one of those strange, mind-bending questions: can fire burn water? And no, it's not magic. It's quantum mechanics simplified, and by the end, you'll see why physics can surprise even the most skeptical mind. I grew up in Far Rockaway, New York, in a house filled with curiosity. My father, a uniformed salesman with an extraordinary love of science, would challenge me with puzzles before I could even spell physics. He'd ask, why is the sky blue? Why does water run downhill? And instead of giving me a direct answer, he taught me to watch, to measure, to reason. That early curiosity, the delight in asking what if, became the engine of my life. It's what led me to Los Alamos during World War II, not just as a mathematician calculating nuclear reactions, but as a problem solver who approached every puzzle with play and imagination. I've always believed that if you want to understand something, you must be willing to question everything, even what seems obvious. Now, let's set the stage. Fire and water, two elements we've all met in our kitchens or camping trips, appear to be enemies. Water extinguishes fire. Fire consumes wood, gasoline, paper, but water, it puts an end to the party. But physics is rarely that simple. Imagine for a moment extreme conditions, water trapped in a sealed environment, subjected to intense heat. What happens then? Steam builds, pressure rises, molecules vibrate wildly. And if the heat is high enough, water itself can become a conductor of energy, creating states of matter that look nothing like the calm haystore we drink. Fire doesn't just vanish, it transforms, and it's exactly this transformation that lies at the heart of the fire-burning water paradox. I have always loved thought experiments. As a young man, I would imagine impossible scenarios and push the boundaries of understanding without ever touching a laboratory setup. I'd picture a spaceship falling into a black hole or a pencil spinning on a table at impossible speeds. Thought experiments are my secret tool, imagination married to the strict rules of physics. In the case of fire and water, we can ask, what if you concentrate enough energy on a small volume of water? Could the heat actually induce reactions we don't normally observe? Could the molecules of water behave in ways that make fire seem to exist within it? Picture this, a droplet of water in a pressure-sealed vessel exposed to a flame hotter than the surface of the sun. The water doesn't just resist, it changes, expanding into superheated steam, ionizing into plasma, allowing energy to propagate in surprising ways. You don't need to do this at home. It's a thought experiment, but it reveals truths about the universe that are far from imaginary. When I was a boy, I loved to dismantle radios and toys just to see how they work. I would create little explosions with chemicals in the backyard, not to destroy, but to observe cause and effect. That same playful curiosity guided me at MIT and later at Princeton. Every experiment I imagined, no matter how impossible, became a way to see the world differently. And in the case of fire and water, imagination meets real physics. Fire, after all, is not a substance, it's energy in motion, a release of heat through chemical reactions. Water is a medium that usually absorbs that energy, but in extreme conditions, water itself can participate in reactions, converting heat into pressure, energy, and even plasma states. It's not magic. It's the careful, delightful interplay of physics. Now let's talk about superheated steam. You've seen a kettle whistle. Steam is water in an excited state. But what if you confine that water, add incredible heat, and restrict its movement? Suddenly, the molecules move with such intensity that they can strip electrons from atoms, forming plasma. Plasma is sometimes called the fourth state of matter, and it behaves differently from the water you poured on your barbecue last summer. Fire can exist alongside it, interacting, feeding on energy without the simple putting out effect we expect. That's the mind-bending beauty of physics. The familiar can become extraordinary under the right lens. When I explain these things, I often think about how we teach physics to children. It's tempting to hand out formulas and expect memorization, but the real magic, the real understanding, comes from asking, what if? What if the laws of energy acted differently? What if molecules behaved in ways we don't normally see? That's what I try to instill in my students and what I want to share with you. Physics isn't just a subject, it's a way of seeing. It's about observation, imagination, and relentless curiosity. And curiosity, I can assure you, can be just as exciting as a high-speed particle collision. Here's a story most people don't know. When I was at Caltech, I would sneak into the physics labs late at night, not to experiment officially, but to try things my colleagues deemed too trivial or silly. I'd light small quantities of chemicals, measure reactions, and sometimes blow things up in controlled ways, always observing, always questioning. Those moments weren't about danger, they were about discovery. And that same mindset allows us to explore fire and water today. By imagining extreme scenarios, by asking the impossible, we reveal hidden layers of reality. The beauty of this question, can fire burn water, isn't just in the physics, it's in the mindset. Science isn't only about formulas or equations on a blackboard, it's about curiosity, play, and daring to see the world differently. I want you to picture energy flowing, molecules vibrating, reactions sparking in ways that feel impossible. You'll see that fire and water aren't strictly enemies. They're partners in a complex dynamic dance governed by energy, pressure, and quantum mechanics. Even a simple drop of water under extreme heat can teach us lessons about matter, energy, and the universe itself.
And here's the kicker. All of this can be explored without becoming a professional physicist. You don't need a Nobel Prize to ask bold questions, to imagine impossible scenarios, or to see ordinary phenomena in extraordinary ways. In fact, the best discoveries often come from those who look at the familiar and say, wait a minute, what if I'm wrong? What if there's more here than meets the eye? That was the approach I took throughout my life. From my childhood experiments with radios and chemicals, to my work on quantum electrodynamics and teaching at Caltech.
So as we explore fire and water together, I want you to think like a physicist. Observe, imagine, and never take things at face value. Ask questions that seem silly, impossible, or even nonsensical. Could fire burn water? The answer isn't simple. It's subtle, strange, and utterly fascinating. And along the way, you'll discover something more important than any answer, the power of curiosity itself. It can open doors, spark ideas, and make even the most impossible-sounding questions meaningful. This video will go deeper into the physics of combustion, superheated steam, and plasma. We'll connect these ideas to quantum mechanics, the subtle underpinnings of energy and matter. And we'll see how one of the greatest minds of the 20th century, me, Richard Feynman, approached impossible questions with a sense of play and discovery. By the time you're done, fire and water won't seem as simple as they once did. There'll be a window into the strange, beautiful, and sometimes counterintuitive rules that govern our universe. Fire burning water. Sounds crazy, doesn't it? You've seen it in cartoons, maybe in chemistry demos, but in the real world, most people would say it's impossible. And yet physics tells a different story. I'm Richard Feynman, and today I want to show you how what seems impossible can actually happen. Not because of magic, but because of energy, molecules, and the fascinating laws of the universe. Stick with me and you'll see fire and water in a way that will surprise your intuition, challenge your assumptions, and maybe even make you smile. I always loved questions that didn't have obvious answers. That's what made physics exciting. People look at fire and water and think, that's simple, water stops fire and story. But the universe has a sense of humor, and physics likes to keep us on our toes. Sometimes the simplest questions hide the strangest answers. And that's exactly what I love, poking at the edges, asking questions that others ignored and following curiosity wherever it led. So I want to give you a sense of how I think. As a boy in Far Rockaway, New York, I was endlessly curious. I dismantled radios just to see how they worked. I would watch ants, see how they interacted, and imagine laws of physics governing their tiny societies. My father never told me what to think. He taught me how to notice, how to observe, how to question. That habit became the foundation of everything I did. It carried me through MIT, Princeton, Los Alamos, and Caltech, all the way to the Nobel Prize in Physics. And it's the same curiosity we're going to use today to explore the fire-burning water mystery.
Let me tell you a story that gives you a sense of my playful side. At Los Alamos, where we were working on the Manhattan Project, I had an unusual hobby, safe cracking. Not for mischief, but to understand systems. I loved puzzles, and I brought the same mindset to physics. What looks impossible might just be misunderstood. Later, when I played the bongos in public performances, people thought it was just fun music. But really, I was learning patterns, rhythms, probabilities, the same principles that govern particle behavior. That's the essence of physics. Noticing patterns, seeing connections, asking questions no one else thinks to ask.
So, how does fire meet water? You've been taught that water extinguishes fire, and in most cases, it does. But energy changes everything. Imagine a droplet of water trapped in a tiny sealed container. Now imagine applying an intense focused heat. The water doesn't just sit there. It absorbs energy, molecules vibrate, pressure builds, and something remarkable happens. The water can turn into superheated steam or even plasma. In that state, fire doesn't simply disappear. Energy moves through the system in ways that defy our daily experience. It's subtle, it's strange, and it's beautiful. That's where quantum electrodynamics comes in, where the tiniest interactions between particles dictate behavior that at first glance seems impossible. I love thought experiments. Even as a child, I would imagine impossible situations, spinning moons, falling pencils, particles in a box. Later, as a physicist, I formalized these experiments with math. That's how I approached fire and water. Picture it, water in a sealed chamber, fire applied with extreme heat. What happens at the molecular level? Could energy transform the system into something unexpected? Visualize molecules vibrating, electrons shifting, bonds breaking, and new forms of matter appearing. That's quantum mechanics in action. And the trick is, you don't need to witness the experiment to understand it. You just need curiosity, imagination, and the courage to follow the math where it leads. When I taught physics at Caltech, I would often tell students, you don't have to be afraid of being wrong. You have to be curious. That's the fun part. And it's the same with fire and water. The physics may sound counterintuitive, but it's logical. Energy, pressure, heat, and chemical reactions all follow predictable laws. Laws that I've explored through Feynman diagrams and thought experiments alike. Molecules of water are constantly in motion. Fire, in a sense, is energy looking for a way to express itself. When these two forces meet under extreme conditions, the results are surprising, dramatic, and even visually striking. Here's another story most people don't know. I once demonstrated a superheated liquid experiment in front of my students. No explosions, no chaos, just observation. Water, confined and heated, began to behave unpredictably. Steam surged, pressure increased, molecules ionized. Some students gasped, others were silent, thinking, that can't be right. But it was right. Physics predicted it. And that moment, that thrill of seeing the unexpected is what I live for. That's why a question as simple as can fire burn water is so compelling. It's a doorway into the extraordinary hidden in the ordinary.
Let's not forget how this connects to quantum mechanics. Even the smallest particles, the electrons, protons, photons, follow rules that govern energy transfer. Fire is energy in motion. Water, when sufficiently heated, can become a conduit for that energy in ways that ordinary experience doesn't prepare you for. That's quantum electrodynamics at work. Every collision, every excitation, every tiny interaction has consequences. And when we understand those consequences, the impossible becomes plausible. Fire can burn water not in the everyday sense, but in a precise physics-governed sense that reveals the universe's subtle beauty.
My approach has always been playful. Physics isn't meant to intimidate. It's meant to delight. I want you to imagine, to question, to picture the improbable. That's how real understanding emerges. Safe cracking, bongo drumming, tinkering with radios. They all taught me one thing. Patterns exist, and with curiosity, you can uncover them. Fire and water are no different. By imagining extreme conditions, by thinking like a particle, by following the energy, you uncover a hidden dance of matter. And that's the joy of science. The universe is more creative than you are, and it's ready to surprise you if you pay attention.
Even my colleagues at Los Alamos would shake their heads at my antics. I would ask questions others deemed irrelevant. Why does this happen? Could this reaction occur under extreme conditions? What if I confine the system? Most of the time they ignored me. But sometimes those questions led to insight, not just for me, but for everyone. And that's exactly why asking, can fire burn water, is worth exploring. It's not about danger or spectacle. It's about curiosity, reasoning, and discovery. And that brings us to unexpected outcomes. When water is superheated or ionized, molecules behave in ways that defy intuition. Steam bursts, plasma forms, energy flows in strange patterns. You might say it's chaotic, but it's not randomness. It's the law. Energy and matter follow rules, subtle rules, rules that Feynman diagrams help us visualize. The outcomes are beautiful, surprising, and sometimes explosive, literally. That's the thrill of physics, understanding the rules behind what seems like chaos. Finally, remember this: curiosity is more powerful than knowledge alone. Knowledge tells you what is, curiosity tells you what might be. Questions like, can fire burn water, open doors to discovery, play, and imagination. Ask questions, think differently, explore boldly. That's the way I approached physics, from the Manhattan Project to quantum electrodynamics, from teaching to performing on the bongos. And it's the way you can approach any problem, any mystery, and yes, even fire and water. So what can we take away from all this? Richard Feynman showed us that physics isn't just about equations or textbooks. It's about curiosity, asking the impossible questions, and having fun while exploring the universe. From fire that can burn water, the tiniest particles in quantum mechanics, he reminded us that science is everywhere, and understanding it is a kind of play.
If you enjoyed diving into Feynman's world, make sure to like this video, leave a comment with your favorite mind-bending question, and subscribe to Feynman Flux. There's a whole universe of physics, quantum mechanics, and science inspiration waiting for you right here.
Don't stop now. Click on the next video and keep exploring. Curiosity is contagious, and who knows what amazing ideas you'll discover next.